In this section, 8.1, we're going to solve systems by substitution and elimination. And this is something you started learning in Algebra 1. So this section should be fairly easy, I hope. We're going to talk about definition and classification of linear systems solved by substitution and elimination. Sometimes that's called addition. We've got some larger system equations we're looking at, some applications, and we may or may not use the technology piece. So let's go on and get started. A system with no solution, instead of writing no solution, which like you may have in the past, you're going to say it's inconsistent. A linear system that has at least one solution is called consistent. And one that has infinite solutions is dependent. So those are three things you'll be asked. Is it inconsistent, consistent, or dependent? Depending on whether it has no solution, one solution, or infinite solutions. So let's go on. It says use the method of substitution to solve the system. What you look at for a system that has, for substitution, you see an x or a y without a coefficient in front of it. This has several x's and y's without coefficients in front of them. You take one of the equations and make it either x equals or y equals. So here we've got x equals negative y plus 5. That's the second equation. Then you take and put it in the first equation, which was 2x. So you put the y, negative y plus 5 instead of the x. 2x minus y equals 1. But now we have all y's. And so you distribute your 2. Negative 2y plus 10 minus y equals 1. Then negative 2y plus negative y is negative 3y. You have subtract your 10 across, and so negative 3y equals negative 9. Divide by negative 3, and you get y equals 3. Now we put that back in the first equation to figure out what x is. So where we have negative y plus 5, you have negative 3 plus 5. Okay. Or you can put it back in the equation as it was. I would have just put it back in the one up top. And so you're going to get 2 for x. So you have a point. It's listed as the xy variable point 2, 3 because it's a point on a graph. Alright, now this is the graph that corresponds to that. They've got an equation of both of the lines, and the point of intersection 2, 3 is the solution that you're looking for. Okay, so it says, look at this, again substitution. We've got the x plus 3 equals 3y. That's the one we're going to use. We're going to solve for x. Okay, and so x is equal to 3y minus 3. Then you're going to substitute it into the equation on top, so I'll have negative 2 times 3x minus 3 plus 6y equals 6. Distribute your negative 2. So you have negative 6y plus 6 equals 6y plus 6y equals 6. Well, what happens to the 6y's is they add to be 0, and you end up with 6 equals 6 or 0 equals 0 if you subtract your 6 across. Either way, if you end up with a true statement, then that is a dependent system. Okay? So the system is dependent because it means they're the same equation. And actually, if you graphed it, the lines would just be one on top of the other one. Okay? So if we solve either equation for we can describe the solution set as 3y minus 3 for your x, because see, we found if you go back here, you have x is equal to 3y minus 3, and so that's how you're going to define your x. When we go up here to the putting it as a point, 3y minus 3, and y is your point, and y is an element of the real number set. Or if you solve for y first, you'd have x is equal to x plus 3 over 3. And x is, so whichever one is not an equation, that you add such that that's an element of R. Okay, so use elimination to solve this. Elimination means we're going to have to make one of the variables add to be 0. So if you look at this 3y right here, the y's have opposite signs already, a plus and a minus. If I multiply this by 2, on the whole equation across by 2, I'll get a 6y. So I believe that's what we're going to do. Okay, so we're going to go, I'm going to skip a lot of this writing, but you can go back and look at it if you want to. So what we're going to do is we're going to show what we did, which is we multiplied 2 times equation 1. And so we have 10x plus 6y equals negative 14. 7x minus 6y equals negative 20. When you add these equations together, 10 plus 7 is 17x. 6 plus negative 6 is 0, so the y's aren't there anymore. And negative 14 plus negative 20 is negative 34. Now you just divide by 17 and find out that x is negative 2. Then we go back and plug that into one of our original equations and find out what y is. So we put our negative 2 in for the x and find out that y equals 1. And so our point is negative 2, 1 is the solution of the system. You can go back and take that pair and put it in the equation you did not use to check your answer. It's a good way to check to be sure it's worked, because it has to work for both to be a solution. If it doesn't work for both equations, it's not a solution to the system. So now we've got fractions. We're going to have to multiply by 2 different numbers to make these things add to be 0. So to make these equal 0, we're going to have to pick either x or y. So we're going to multiply equation 1 by 3 and equation 2 by negative 2. We have to multiply by opposite signs because we don't have already a set of equations that have opposite signs. So multiplying by 3 and by negative 2, we end up with this. It accomplished a couple things. 2 got rid of the fraction in the second equation, but it also allowed us to make our x's add to be 0. But it also makes our y's add to be 0. So we end up with 0 equals negative 1. Now before, remember, we ended up with 0 equals 0 or 6 equals 6. That was a true statement, and that meant it was dependent. This is a false statement. 0 can never be equal to negative 1 or any other number. They're 2 very distinct values. So this is a false statement. So this is the type of thing where you have an inconsistent system. There is no solution to it. Okay? So graphically, when we look at these, there's our parallel lines. It's a false statement. The system is inconsistent, and that means they're parallel lines. They will never intersect. Not even at one point. All right, now this is a larger system. This is 3 variables, 3 equations. We'd kind of do the same thing. You're going to make one of the variables add to be 0, but we're going to add just 2 of them at a time, not all 3 of them at the same time. So we're going to add the first equation to the second equation, or the third, and you eliminate anything, but in this case all the z's have a coefficient of 1, so it makes the z's a little bit easier to eliminate. So we're going to start by adding equation 1 and 2, and you get 4x plus 4y equals 4. Now we can add 2 more equations. One of them will be the same as the first set, but the third equation will be involved. So we're going to add equation 1 and 3. Chose those because the z's have opposite signs in both of them. So we have negative x plus 3y equals 11. Now we take those 2 equations and add them together. And now we have to figure out a multiple to make one of those equations, one of those variables cancel out. So now we're back to what we did earlier with two variables and two equations. If we multiply the second equation by 4, then our x's will add to be 0. And so now we have 16y equals 48. And so we can figure out that y is 3. Then you're going to back substitute to find out what x is. Negative x plus 3 times 3 is equal to 11 becomes negative x is equal to negative x plus 9 equals 11. So x is negative 2. Now we have a value for x and a value for y. We go back to one of our first equations and figure out what z is. Okay. And then you can check it in the other two if you need to. Check the negative 2, 3, and 7 to make sure it works for all three systems. And you write it as a point, an ordered triple, an x, a y, and a z.